So our next speaker is Margarita Vald, who will be presenting her joint work with Adi Akavya and Neta Oren and Boaz Safib. She'll be speaking about compact storage for homomorphic encryption.
Okay, good. Thank you. So I want just first to tell you that this project started when we wanted to move some application actually to work over encrypted data and to eliminate access to sensitive data. And we looked what we need to do in order to make the whole pipeline secure. And we realized that actually to do that, we're missing one thing. We need to take care of the storage as well. We cannot move to work over, like run machine learning models over encrypted data without taking care of the ciphertext expansion that comes with homomorphic encryption. Okay, so I don't need to tell you about sensitive data and privacy threats, and companies are incentivized to address these threats, basically. And the idea is to follow the principle of least privilege, basically, and to reduce the attack surface as much as they can. And the idea is to give access to applications to sensitive data only if it's essential. Yeah. Okay. So for this, there is a very useful tool, which is a homomorphic encryption that enables computing over encrypted data, right? We can encrypt the data, give it to the server, to the computing server, and the server will just evaluate, perform the computation homomorphically, and send to the end application the result, who has access to the secret key she can decrypt. And semantic security guarantees that the server has no idea what's the data, but correctness, to ensure correctness, we need additional, of course, tools. Okay, perfect. But the key advantage that we want to take advantage of is the low communication. All of these things is independent of course, the function we want to compute, and the function can be very complicated. Okay, so to understand how we can deploy it, basically, to use it, we need first to understand how the enterprise architecture, real-world architecture, big companies look like. Okay? So we have a lot of data producers, and they are collecting data, let's say application and user applications, and they're going to store this data in a centralized storage called the data lake. And the sensitive data is going to be AES encrypted, and on the other hand, we have a lot of data consumers that are using this data to perform some computations, and they have access to the secret key, decrypt the data, and use the data for the computation. The problem with that is that it's enough to break into one of these applications, into these data consumers, in order to get access to the whole data of the company, right? So the idea here is to use homomorphic encryption and eliminate their access to the clear text data, but instead of, they will actually fetch the data homomorphically encrypted and just compute on this. And now, if any of this application is being breached, you see only encrypted data, which is fine. Okay, and I want to say that there will be a small set of authorized entities that will be able to decrypt the data. Okay, and the key gain, of course, that we reduce the attack surface and the access to sensitive data. Okay, so it's very appealing and simple, which is also good. Simple is good, but is it ready to deploy it in practice in company? So, of course, homomorphic encryption has two bottlenecks. One is time complexity, and it has significant overheads. This is one. But I want to say that there is a lot of progress in recent years to make homomorphic encryption actually usable. There is now work on dedicated hardware, accelerators, also libraries become more and more efficient, and also concrete solutions for ML, for example, algorithms that can be reasonable, that take reasonable time over encrypted data. Okay, and there is another drawback, that it's the ciphertext expansion. In terms of storage, currently the data is stored in AES, but now if I want to move to work with FAG, then it would be 10, the overhead would be 10 to the 4x, between 10x to 10 to the 4. And that it depends if you batch or not. But in reality, data is used by many applications, same data with different combinations. So I cannot really determine upon storage what to batch with what, because I cannot feed it in to all use cases later. So basically, I won't be able to enjoy the batch. Okay, so in today's talk, I'm going to focus on how to eliminate the storage overhead, how I can store efficiently with no storage overhead and still let the applications, the data consumers fetch the data homomorphically encrypted. Okay? And of course, if I want to deploy it in production, I need it to be relatively fast, yes? Like reasonably fast. Machine learning works on millions of data points, so I cannot have a big overhead in time. So one approach that was taken since 2011 is to actually store AES encrypted data and transform it by homomorphically evaluating the decryption circuit to ciphertext under homomorphic encryption. Okay? And so there are implementation of these by Gentry, Halevi, and Smart, and others. And also there are string ciphers that are specifically designed to have low multiplication depth to be efficient in this approach. Okay? And here I want to say that although there is a lot of progress, it's still too slow for vast amounts of data. We're talking about millions of data points for machine learning training algorithm. Okay, and also another thing that I want to say that it's something that industrial, usually to be compliant, you need to store the data using AES. Data at rest need to be stored, encrypted, sensitive data encrypted using standardized encryption, which is AES. Another approach is RAID 1 homomorphic encryption. And here it does packing and compressing of many data items into a single ciphertext. And I want to say here that the compressed ciphertext, after compression, they have limited homomorphism. So for general purpose computation, this is not suitable, but I do want to say that it's a beautiful line of works and it is suitable for many nice applications. Okay. So if we want to get back the homomorphism, the original homomorphism, we need to do uncompressing, and this is very slow. And again, going back to the packing thing, that we need to here also we need to determine upon storage exactly the packing. What data we pack together, okay, which does not allow us the cherry picking that we really want. So we take a different approach in this work, and we design a protocol for storage and retrieval of HE ciphertext, but we use two server model. Okay? We do the retrieval in the two server. The storage is a single data producer, but the retrieval is in the two server model. And our protocol has no storage overhead at all. I'll call it RAID 1, similar to the works of RAID 1 AG. It gives data privacy under the assumption of non-colluding servers. And it has unrestricted homomorphism. It means that what homomorphic encryption scheme I'll pick, this is the homomorphism that I will get for the retrieved ciphertext. And it's fast. It is only 2 times slower than storing and retrieving HE ciphertext directly. Okay, so the trivial approach is to store and retrieve ciphertext in HE. So this is only 2 times slower, and it has dynamic control. What do I mean by that? I can pick the encryption scheme, its parameters, everything, what batch together only upon retrieval. The storage is completely independent of the encryption scheme and its parameters, so it has full dynamic control. Okay, good. So to do that, we develop a new tool that is a secret sharing scheme. with homomorphic reconstruction over the reals. And it has fast homomorphic reconstruction. And I'll tell you why I'm interested to talk about reals is because one thing is that we want to use CKKS. And CKKS use arithmetic, plaintext arithmetic over the reals. CKKS is fast and we want to use it. And second is that real world data is usually, at least for machine, is usually reals, and for machine learning, it is scaled even to between 0 and 1, usually. Okay. So we're interested in reals. So we developed a secret sharing scheme for numbers between 0 and 1. And it requires only additive homomorphism over the reals, and it's very fast, the CKKS. In particular, our secret sharing scheme does not need to do modulo reduction in the reconstruction phase. Okay, and why this is important? Because previous schemes did modulo reduction, both in sharing and reconstruction. And if I want to use CKKS that does not support it, it does arithmetic over the reals, this would be extremely slow doing modulo 1. If you want in integers, actually, you can take additive secret sharing and use BGB. But we're interested in numbers that are reals. Okay. So let me show you our construction. When I started? Huh? Okay, perfect. So what is secret sharing? Just to say, I'm sure you know, it's a method to split secret into shares such that each share does not reveal any information about the secret. But if I combine the shares, I can reconstruct the secret. Not in all schemes I need all the shares. Sometimes I need a subset of them. But let me give you an example. This is Shor-Kushilevitz secret sharing between 0 and for numbers between 0 and 1. What they do to share, they pick a random mask, and then they take the secret and add to this mask and do modulo 1. Basically, it's taking the fractional part. Okay, so the share number 1 is the mask, and share number 2 is the fractional part, random. Okay, and to reconstruct the first share, I call it S1. Given S1 and S2, which is the 2 shares, we take S2 minus S1 and do modulo 1. Okay, that's simple. Okay, what we do is somewhat similar to Shor-Kushilevitz, just getting rid of the modulo 1. So to share a secret, we take a random mask R and also a bit B. And to compute the second share, we take X plus the masks, the secret plus the mask modulo 1, which is the fractional part, and also randomly flip the integral part. That's what we do here. Okay, and I'll call it X int and X frac. What I want to say here that it will be important for the storage that each share, the size of each share is exactly the size of the secret itself. So it will be useful. And if I want to reconstruct, given R and B and S frac and S in, what I'm doing basically is taking the fractional part, subtracting the mask, and flipping the thing. Believe me, the math goes through. I won't do the math here, but what I want to say is that there is no modulo 1 anymore. And moreover, it is a degree 1 polynomial if I look on S int and S frac as the unknowns. So what it gives me is that I can actually evaluate this also when S int and S frac are encrypted. Okay? So, and this would be really fast if I encrypt it with CKKS, and then it will be extremely fast. So I will just call it linear homomorphic reconstruction. And the first thing, and regarding the sharing algorithm, I want to also emphasize that the first share is random. So it has random first share, and many secret sharing schemes has random first share. And this property is very nice later when we want to construct storage protocol from this secret sharing. So let me tell you what we're going to construct, just to make sure. I want this protocol to be in realistic system. So I want to store a data item X in a database location. that has some index, okay? I'm storing it in a table with some name and in some row with some location, okay? So this is the index where I'm storing the data. Okay, and also when I'm fetching the data, I want to fetch some data from a location in the database, okay? So it has some index, and as I said, retrieval, I'm going to retrieve an encryption of X under homomorphic encryption in the two-server model. Good. So the approach is to use TRFs and 2 out of 2 secret sharing. And the protocol is generic, but we're instantiated later with our secret sharing. So I'm using a secret sharing, 2 out of 2 secret sharing with random first share and linear homomorphic reconstruction. And the linear homomorphic reconstruction is just for efficiency, okay? It's not the general, like a theorem does not require it to be linear homomorphic reconstruction. Okay, so just to say, so the idea is to store the second share, and the first share is going to be pseudo-randomly generated on the fly. And in the retrieval phase, I'll have 2 servers. One server is going to fetch the share from the database and encrypt it homomorphically, and the second server is going to homomorphically reconstruct on the encrypted share. So I'll give you the details, how it looks. So we have the data producer holding a key to a PRF function, and he's going to compute the PRF on the index to get the first share. This is a pseudo-random value, and then to compute the second share. Because it's random first share, I can compute the second share when the first share is already determined, okay? On the input X and store S2. And to retrieve the first share, the computing server here is also holding the same PRF key. I want just to mention here, in reality, this is not a problem because we can have each data producer to have a PRF key. And the computing servers in the system using authorization and authentication, they can access, get authorization to access this PRF key. And you will store it in KMS. Okay, this is usually what's going on. So he will compute S1 and then send the index to the auxiliary service, which is going to fetch and print, as I said. And just the computing server is going to homomorphically reconstruct X and compute over the encrypted data. Very simple. So, as I said, in general, the theorem, I need basically secret sharing that is compatible with the encryption scheme. So let's say I have a homomorphic, I need an encryption scheme with homomorphic addition over some ring, and the secret sharing needs to be compatible. I wrote here for efficiency degree 1 polynomial, but in general, the reconstruction circuit with S1 hardwired needs to be in the homomorphism set. That's all I need. And the protocol, the generic protocol that I just showed is satisfy correctness. If I store an item X and fetch from the same index, I retrieve from the same index, I will get an encryption of X. It is private in a sense that if one of the servers is corrupted, his view is indistinguishable whether the data that was stored is X0 or X1, doesn't, and also compact. So the storage that I need is S2, the second share. Very simple. So what I do with that, one thing is I instantiate it to get rate 1, basically no storage overhead, storage for homomorphic encryption over the rails. How I do it? I use CKKS and our secret sharing scheme. And I get no overhead because the second share, the shares in our scheme is exactly the same size as the input, the secret X. And I also can do it for ZN. So I can have no overhead storage for ZN if I instantiate it, as I said, with additive secret sharing and BGV. Okay, I think I need 1 more minute, 2 more minutes. So we implemented the protocol, and I'll just say briefly about that. I'm not going to go over the numbers. So we implemented it with our secret sharing and Microsoft Seal for CKKS in AWS in S3 storage. And as I said, in terms of storage, we get, depends if it's batched or not batched, we get between 10x and 10 to the 4x. Running time, we tested it until with 2 million data points, various sizes of various data sets, and we get amortized 10 microseconds about for retrieval. And then only one thing I want to say here is that everything, the retrieval phase is negligible relative to actually computing over encrypted data. So here is an example that we did. We ran evaluation, decision trees, prediction on a forest of 64 trees, depth free, and this took 10 milliseconds, and this was 9 microseconds. So it's really negligible. So don't worry about retrieval. That's it. So just to summarize, we propose a compact storage with privacy preserving retrieval in a 2-server model, no overhead, fast running time, and fully dynamic control over the scheme and the parameters and cherry picking of the data. Using a nice secret sharing scheme with no modules for the reals and implementing it on AWS. Thank you. I'm so sorry.
What did you use for the read? The fixed point couplers or floating point couplers, or how did you implement the real numbers?
I'm sorry?
What did you said you use it for real numbers, but like how did you implement real numbers? Like,
oh, good question. So I didn't say we use fixed precision, okay? But when we store it, it floats, but fixed precision. Usually for, you know, by the name of the table, you usually know how much precision you need the salary. Oh, yeah.
Usual question, like in your context, how do you justify the non-collusion assumption between the servers?
So, okay, I want to say 2 things about it. Great question. To repeat the question for the Zoom, or yeah, how I justify the non-colluding servers. So I want to say 2 things. Basically, the servers are not equal power, right? If we look on the servers, the auxiliary service is a service. It has dedicated functionality, very simple. Input, output, it does only one thing. It's not a general purpose computation. So in reality, you can better protect such things. And also, we kind of used to this. If you think about KMS, right? Key management service, right? What you can do, either give your keys to Amazon, or split the trust between few servers, split your keys, kind of signature between few. So we kind of also, like, it's, in a sense, for some tasks, it's the best you can do. But it's, you know, time, we also need it to be at least near real time in terms of performance. Hope it answers your question.
Okay, so let's thank the speaker again for the talk.